Thanks everyone. So today we are going to discuss about our new topic. The new topic of this chapter, which is the pure hydrocarbons. We have understood that hydrocarbons. We have understood already that a hydrocarbon is essentially of two types. Hydrocarbons are essentially of two types: pure hydrocarbons and some derivative hydrocarbons. Um, for example, if you just take understanding of the pure hydrocarbons, these are hydrocarbons which are purely made up of carbon and hydrogen. There's no other atom used, there's no other element used, only carbon and hydrogen. But if we talk about derivatives, we have with carbon and hydrogen some other elements like oxygen, nitrogen, sulfur, phosphorus, um, so forth and so on. So those are derivative functional groups. Derivative functional groups. So we are going to study those as well, but in today's class we are going to look into uh, pure hydrocarbons. Now pure hydrocarbons is example of alkane, it is example of alkene, alkyne and benzene. So if you just take the structure of alkane, alkene, alkyne, all of them are straight chain hydrocarbons, which means they form a straight chain. They do not form a closed ring. They form an open ring, which is the pure hydrocarbon, which is the type of pure hydrocarbon. So essentially, pure hydrocarbons involve the straight chain hydrocarbons, which is also known as aliphatic hydrocarbons, and the second type is benzene, which is aromatic hydrocarbon. Now we are going to discuss benzene in another class. For this class, we are going to look into aliphatic hydrocarbons, which is alkane, alkene, alkene. So let's just move on to the today's class. Here, over here, we are just going to look into some basic understanding of what alkane, alkene, alkyne are actually. You just see alkane. Alkane are also known as paraffins, because they have a high, para means high and affin means affinity, so they have a high affinity, towards hydrogen. They have a greater love for hydrogen, due to which these are known as paraffins as well. And they are also known as saturated hydrocarbons. Why do we call them saturated? Because they are all surrounded by hydrogen atoms. On their all of their four sides there is a hydrogen atom present. So if you just take its empirical formula, it is more like this: CnH2n plus 2. So this is a formula, and alongside that, when it comes to structure, we just look into the structure. We have, let's say, if this is I'm just drawing the structure of ethane, right? So I'm drawing the structure of ethane. Over here we've got two carbons joined together for a single bond, and then we have hydrogen atoms all surrounding it. Essentially they have a single bond. So when they're now, if you just look into this structure, this is a structural formula. Now when I look into its basic structure, it will have all four orbitals, all four atomic orbitals, 1s and 3p, hybridized into sp3, into 4 sp3 hybridized orbital. So they basically undergo hybridization to form 4 sp3 hybridized orbital, and because they form 4 sp3 hybridized orbital, the structure which they get is tetrahedral, and the bond angle is essentially 109 centigrade. All right, so now let's just look into the structure of ethane. If you just take example of all of its bonds, it is the hydrocarbon which only forms sigma bond. There are no pi bonds involved in alkanes, due to which alkanes do not have much of the reactive characteristics. If I were to, make it understandable in terms of a pure structure, here it is. Let's say this is carbon with all of its 4 electrons on each side. This is hydrogen, one hydrogen here, one hydrogen here, and one hydrogen here. So what there would be a bond here, there will be a bond here, there will be a bond here, and there will be a bond. Oops, there will be a bond here, a bond here. So in that way, these would be the bonds created. If we take the structure, it would be an sp3s, 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 sp3s. And if I'm going to, compare the carbon to hydrogen bond in alkane with the carbon to carbon bond in alkane, then at that point the bond which would be the bond which would be more stronger, the bond which would be more stronger would be the carbon to hydrogen bond. Carbon to hydrogen bond will be more stronger. Why do I say that? Why do I say that? I say that because carbon to hydrogen bond is having s orbital and sp3 orbital joining. Now why, and while if you just, take carbon to carbon bond, it is having sp3 and sp3. We know that in sp3 we have 25% s characters, while in s there is 100% s character. So uh, because s orbital is having more attraction, more because it is more closer to the nucleus, it is having more nuclear attraction attracting it, due to which more nuclear attraction attracting it in hydrogen would comparatively make carbon to hydrogen stronger than carbon to carbon bond. All right, so let's just, move on to the next part, which is its properties. So if we just talk about all of its properties, number one property is all of them are colorless or odorless. Whether it's gas, liquid, or waxy solid, they are colorless or odorless. Carbon 1 to carbon 5, they are gases. Carbon 1 to 5, they are gases. Carbon 6 to carbon 17, they are liquids. And carbon 18 onwards, carbon 18 onwards, they are waxy solids. All right, and if you just talk about the melting point, the melting and boiling point, the melting point essentially increases with the number of methylene group. With each methylene group, there will be 20 to 30 degree centigrade rise in the melting point. So this is an important point. For example, if you just, take some ethane, we take ethane and then we, add a methylene group in it, then it's going to raise the temperature by 20 to 30 centigrade. And straight chain hydrocarbons are having higher melting point than than the branch chain hydrocarbon. Straight chain hydrocarbon, also known as normal alkanes, have a greater melting and boiling point than isoalkanes. So how can we consider that? For example, a butane is having its melting point minus 0.5 centigrade, but isobutane is having its melting point as minus 11.5 centigrade. So this is something that needs to be considered. If there's a normal chain, if you just, take a normal chain, for example, if I take, let's say this is a propane, right? So I take this propane, or let me just make it a bit more complex. Let's say if I take a pentane, let's say I take a pentane, right? So essentially this is essentially a straight chain pentane, also known as N-pentane. And comparatively, I'm just taking um an isopentane, an isopentane. Now, if you just look into this, what we'll actually get is the side chain makes the side chain makes the alkane more stable. The side chain makes the alkane more stable, due to which the isoalkanes would have a greater melting point than an alkane. And for example, isobutane has zero point 0.5 centigrade temperature as a melting point, and for n alkanes it is 11, minus 11.5 centigrade. So now let's just move on to the next part, which is the preparations of alkane. How can we prepare alkane? So generally there are six methods of preparing alkanes. Number one method is through hydrogenation. What actually hydrogenation is? Addition of hydrogen. When we basically take hydrogen gas and we add it to an alkene or alkyne in the presence of the catalyst, which is nickel, palladium, platinum, at a very high degree temperature, 200 to 300 centigrade, we basically get alkane. So this is a basic reaction. And secondly, we are having another reaction, dehydrohalogenation, in which we take out um, dehalogenation, in which we basically take out the halogen atom from alkyl halides. We take alkyl halide and then we add an aqueous we add alkyl halide and then we use zinc in an aqueous acid, due to which we basically get an alkane and the zinc halide. So this is the entire reaction. And then we have hydrogenolysis. Of that's another method of getting the alkane, such that we take an alkyl halide and we perform its hydrogenolysis. We provided hydrogen with a bond breakage of hydrogen, that is done in the presence of palladium charcoal catalyst. So that's the results in formation of alkane and hydrogen halide. Alright, and another method which is pretty important is decarboxylation. Decarboxylation is a process where we take a sodium salt, we take a sodium or potassium salt of a carboxylic acid, essentially it can be monocarboxylic acid. So if we, let's say if we take sodium salt of an acid and then we react it with sodium hydroxide, in the sodium hydroxide, or also known as lime water with quick lime, also known as caustic soda with quick lime as a catalyst, due to which we will get the alkane. After that, we are having another method which is known as Cobb's electrolytic method. Cobb's electrolytic method is a electrolytic process in which we basically use a sodium or potassium salt of a monocarboxylic acid, and in the result at anode we get an alkane. And what type of alkane is it? It's a symmetrical alkane, which is a symmetrical alkane produced. Symmetrical alkane. And essentially we have at anode the production of free radicals, and those free radicals react with each other in order to produce the alkane. And at cathode we have the production of hydroxide, which combine with potassium or sodium in order to produce the potassium hydroxide. And this reaction has a limited uses because of the energy it takes, as well as this lack of product of interest. Now let's just move on to another part, which is reduction reactions. Now there are two major reduction reactions which are needed to be understood. Number one is the Clemmensen reduction reaction. When we basically take, let's say, a ketone, let's say we take acetone. We take acetone and then we use zinc amalgam in the presence of HCl. Then it will essentially produce a propane. It will essentially produce an alkane, a propane. And when we are going to reduce acetaldehyde in the presence of hydrazine and potassium hydroxide at 200 centigrade, it's going to make ethane. So these are two essential reactions that need to be understood. After that, we have Grignard's reagent. Grignard's reagent, it was first discovered by Victor Grignard in the early 1920, and for which he also received a Nobel Prize as well. Basically, Grignard's reagent is made up of this. This is a Grignard reagent. There's a magnesium atom which is bonded with methyl group and a halide group. That's a Grignard's reagent, and that is known as an organometallic compound. We are going to study that in future as well. And that organometallic compound can produce various is of very important uses. It can produce various industrial products. It can even produce alkanes. So whenever you're going to put Grignard's reagent, methyl magnesium bromide, for example, uh, in water or dilute acid, at that point we will get methane, and we'll get magnesium, bromo magnesium hydroxide. And alongside that, there's an important point to be considered, that organometallic compounds such as the Grignard's reagent are extremely reactive, due to which we always use dry anhydrous ether, as a solution, anhydrous ether as a solvent, so that there should not be any sort of chemical reaction, any sort of explosion essentially. Now let's just move on to another important part, which is the reactions that the alkane perform. Now if we just talk about the reactions alkane perform, it number one involves combustion. Combustion is pretty simple. When we are going to burn methane in presence of oxygen, it's going to produce an orange flame, and that's what produce, of course, carbon dioxide and water and the heat of combustion. Now an important point to be considered over here is that when 1 mole of hydrocarbon is burnt in the presence of oxygen, is combusted, then it's going to produce a heat which is known as heat of combustion. Then the heat which is evolved is known as heat of combustion, and that heat of combustion for methane is 891 kilojoule per mole. Now let's just move on to another part, which is the oxidation. Now there are two types of oxidation. If you just take example of oops if you just take example of again methane, we will basically we can actually whenever we are going to burn methane in excess of oxygen, whenever we are going to burn methane in the excess of oxygen, it's going to produce this carbon dioxide, water, 891 kilojoule per mole. But let's say if I don't uh, provide enough oxygen, I provide limited amount of oxygen, at that point when I burn methane in a limited amount of oxygen, it's going to produce carbon monoxide, carbon black, and water. Now one more thing to be considered over here is that uh, within this reaction, the carbon monoxide gas produced is very harmful for humans because it has a greater affinity for hemoglobin to attach, which reduces the oxygen carrying capability of the blood. And due to this reason, it is known as a silent killer. Silent killer. Now let's just move on to another part, which is incomplete oxidation. Basically, this is known as incomplete oxidation. Whenever we are having limited supply of oxygen, we get carbon monoxide, carbon black, and water. This is known as incomplete oxidation. Now let's just move on to the catalytic oxidation. This is the oxidation which is done in presence of a catalyst at a very high temperature, at a very high pressure, such that we get an oxygen source. This oxygen source can be we can obtain it from, let's say, we can obtain nascent oxygen from oxidizing agents, potassium permanganate oxide. Uh, so we just take uh, you know but essentially we do not use it because potassium permanganate oxide does not oxidize alkanes. Potassium permanganate oxide does not oxidize alkane. It only oxidizes those pure hydrocarbons which are having a pi bond, alkene, alkyne, and benzene, but not in alkane. Oops, benzene. Alright. So right after this, let's just understand this important concept. When methane is oxidized in at this temperature, 400 to 400 centigrade, 200 atm, then we get alcohol. When alcohol is oxidized at the same temperature and pressure, we get aldehyde. When aldehyde is done oxidized at the same temperature pressure with the same conditions, it will produce an acid. And when an acid is oxidized at 200 centigrade and 200 atm, it will produce carbon dioxide. This is something really important to understand. All right, let's now just move on to nitration process. Process of nitration is again pretty simple. We take a source of nitrogen group, nitro group, NO2 group. This is basically known as a nitro group. We take this nitro group containing compound and we react it at a 450 centigrade at vapor phase nitration. This is also known as vapor phase nitration because at 450 centigrade the nitro group does not exist in the form of liquid or solid. It rather exists in the form of in the form of vapors of nitro group, which join with methane in order to produce the nitromethane. All right. So now let's just move on to another important topic. It's the last topic, but that's pretty essential. That is the free radical substitution. There are two essential fissions that happen. The two essential fissions that happen, which number one involve the homolytic fission, and number two involve the heterolytic fission. Fission means the split of electrons. So that electrons can be divided from an atom in two ways. For example, let's say if I take hmm, let's say if I take uh, a chlorine molecule. This is a chlorine molecule. Oops. Let me just make the electrons. Two electrons here, two electrons here, two electrons here, two electrons here, and there's another chlorine molecule. Here are the electrons of the other chlorine molecule, and this is how we have made the bond. Alright, so now we have basically made the bond between two chlorine molecules. I mean, like it does not make sense. The diagram does not make sense, essentially. So I'm going to mark it over here because these are actually having a covalent bond, so they are actually sharing the number of electrons. All right. So, for example, this is a compound which is chlorine molecule. Now, this chlorine molecule, what I actually do is I provide it with UV radiations. I provide it with UV rays, right? I provide it with UV light. So, in that way, what actually happens is by absorbing UV light, the chlorine molecule becomes unstable. And that chlorine molecule basically, what it does is it breaks apart from the middle. It breaks apart from the middle, and then it causes to have an equal share of electrons. It causes to have an equal share of electrons, such that in middle there were two electrons, but when the bond breakage happened, both of these electrons were shared equally. These electrons which were previously shared with them are then divided equally, which is known as the homolytic fission. Homo means same because there is the same number of electrons which each atom receives, due to which it is known as homolytic fission. Now, uh, this this chemical species which is now made as a result of homolytic fission, is very unstable, and this is known as a free radical. Very unstable, and that is known as a free radical. So homolytic fission produces free radical in a nutshell. Now let's move on to heterolytic fission. Let's say if I take hydrogen chloride. This is hydrogen chloride. Let me draw hydrogen atom here. Uh, oops, hydrogen atom here. The chlorine. All right. So this is hydrogen chloride. Now, if I just take hydrolytic fission, it is basically the conventional bond breakage. The bond breakage which usually happens in covalent, in the breakage of covalent bond, in the breakage of ionic bond, is the heterolytic fission. Now, this is a conventional bond. There is nothing special in it. I mean, like it's a simple covalent bond, right? It's a polar covalent bond actually. So, what I actually do is, what I actually do is, I provide it with energy, and at that point, one atom is having, this was a shared pair of electron, this was the a bond pair. One atom will be having no bond pair, and the other atom will be having the entire bond pair. One atom is having no bond pair, and other atom is having the entire bond pair. Due to this, one atom gains a positive charge, other atom gains a negative charge. This process is known as the conventional bond breakage, and that's what actually happens when we form covalent bonds and ionic bonds, and this process leads to the formation of ions. Um, Essentially, it can be ions, but when we discuss it in terms of organic compounds, these ions can also be called as an electron deficit species, which is known as an electrophile, and an electron withdrawing species, which is known as a nucleophile. For example, if there are two, let's say if there are two, uh, there are two atoms, right? Hydrogen and chlorine. Hydrogen gets no electron, due to which it can now accept electron. It has now the capability to accept electron, love electron, due to which it is now an electrophile. But chlorine on the other hand side has a negative charge. It does not want electron at all. It's already filled with electron, but has the capability to give electron. So it's an electron withdrawing group, but not an electron deficit group, due to which it would be a nucleophile. That's it. So in short, heterolytic fission produces electrophile and nucleophile, and homolytic fission produces free radicals. Alright, let's just move on to this essential concept. Over here, the if you just discuss the halogenation process in alkane, that occurs through a substitution reaction, and that substitution reaction is a free radical substitution reaction. So why did I tell you the entire story of homolytic and heterolytic fission? Because the free radicals which are formed are through homolytic fission, and those free radicals are going to be used in this halogenation process. So let's just understand this. There are three major steps of substitution. Number one step of substitution is initiation, which means that we are going to do the same step. We are going to perform a homolytic fission, where we are going to provide UV rays. I provided with UV rays, indicated in the form of H nu, and when I'm going to provide UV rays, homolytic fission will happen, and there would be chlorine free radicals formed. Now what actually happened is the process initiated. The process initiated, chlorine free radicals are formed. Second step is propagation. Propagation generally means when you are propagating or expanding something in magnitude, right? So let's say if I take chlorine free radical and I react it with methane, then what actually chlorine will do is, chlorine is itself unstable. What it will actually do is it will make methane, it will make this methyl group unstable. It will make this methyl group unstable and make itself stable by bonding with hydrogen, due to which it will form HCl, and alongside that it will give an unpaired electron to methyl, due to which methyl will become a free radical. It was unstable, it made methyl group unstable, in order to make itself stable. So H and Cl formed a bond, forming HCl acid, hydrochloric acid, while methyl converted into a free radical. Alright. Um, After that, the reaction did not stop here. Methyl free radical now reacted with another chlorine molecule. Methyl reacted with another chlorine molecule, and at that point, chlorine reacted with methyl to form methyl chloride, and again the chlorine free radical was produced. Essentially, the process involves the propagation of free radicals. The process involves propagation of free radicals. There's one unstable species which basically causes another species to become unstable. In that way, more and more of new compounds are new halogenated compounds are going to be formed in propagation. Now, final step is termination. What the termination is, what actually happens in termination is, within propagation we basically got the methyl free radical which reacts with chlorine to produce chlorine free radical. There is chlorine free radical which reacts with methane to produce methyl free radical, and there are two methyl free radicals which essentially react with each other to produce ethane. So what actually happens in termination stages, when two free radicals react with each other, they basically complete the process. They complete the entire process of halogenation. For example, let's say this is methyl group, methyl free radical, this is chlorine free radical. Both of these are free radicals. When they combine, both of them become stable, and they form they terminate this process, they end this process. And then we have another example of termination as well. If we just having methyl group and methyl group, then they methyl free radicals combining together, it will produce anything. So this is all about it. Now let's just move on to alkenes. Alkenes are again pretty simple. Alkenes are also known as olefins because they are oil producing substances, and they are having the formula CnH2n, and they are having a double bond, such that one bond is sigma bond, other bond is pi bond. If we just talk about their structure is in such a manner that they are having sp2 hybridized orbital, which makes a trigonal planar shape, a trigonal planar shape. And let's just understand what actually happens. One s orbital and two p orbital combine together to form the sp2 hybridized orbital, and rest of the one p orbital basically undergoes rest of the one p orbital goes to form a pi bond. So let's just draw the structure. Let's say if this is one orbital, this is another orbital, hybridized orbital, and there is another sp2 hybridized orbital. Right. So this is basically sp2 hybridized orbital. This is an sp2 hybridized orbital. This is sp2 hybridized orbital. And now I'm going to draw the the atomic orbital p for this atom. Now let's just draw it for this atom as well. So sp2, sp2, and this is a p orbital. Now let's understand this, that this orbital is sp2, this orbital is sp2, and rest so there's one sp2 sp2 bond, There are two bonds which are sp2 joining with s. Let me just mark it with a different color. This is, let's say, s orbital. This is an s orbital of hydrogen. All right, the sizes may vary, but that's the s orbital. All right, so basically these are the s orbitals which are joining with hydrogen as well. Hydrogen. All right, so this is the entire structure. Now sp2 there is one sp2 bond which is a sigma bond. There is sp2s bond, sp2s bond, which is again a sigma bond. This is also a sigma bond, this is a sigma bond, a sigma bond. But there are two pi bonds. There are two pi orbitals which are there are two p orbitals which form a single pi bond. So this bond which is going to be formed, this bond which is going to be formed in a parallel manner, the bond which is going to be formed in parallel manner would be a pi bond. This will be a pi bond, and that bond, since it is parallel, it will be a weaker bond. It is a weaker bond, and that's the reason it makes alkene highly reactive. It is having one pi bond which makes it pretty reactive. So this is all about the structure of alkene. Now let's just understand one more thing over here. One more thing to understand over here is its general properties. So if we just talk about its general properties, from C2, it's the lowest member is ethene, because of course with one carbon we cannot form a double bond. So C2 to C5 gases, they are gases, and C6 to C15 liquids. Greater than C15 or from C16 onwards, they are solids. Now if we just talk about their characteristics, they have a pi bond, due to which they have a smell. They have a characteristic smell. They have a characteristic smell. They have a sweetish taste. They have a characteristic smell. They have a sweetish taste, a characteristic smell. They have a characteristic smell. There's a sweetish taste, and they are having a characteristic color as well because of the pi bond. All right. So let's just move on to its preparations. It has got only one method. There's I know there is uh, a lot to talk about its preparation. So if you just take its first method, it is the dehydrohalogenation. Dehydrohalogenation. Dehydrohalogenation is simply the removal of hydrogen halide, removal of hydrogen and halide group from the alkane in order to produce alkene. For that we use alcoholic potassium hydroxide, due to which we get the for which we get the alkene. After that we have dehydration of alcohol. For if we just talk about its procedure, essentially we take an alcohol and then we dehydrate it with the help of a dehydrating agent, and we get an alkene. So for the general purpose we use aluminum oxide at a temperature of around 340 to 450 centigrade in order to produce alkene. But again, it can vary from uh, alcohol to alcohol. Depending on the type of alcohol, we need to use different dehydrating agents, and we need to use different temperatures as well. Dehydrating agents involve phosphorus pentoxide, sulfuric acid, phosphoric acid. All of these are dehydrating agents. On the other side, on the other hand side, if you just talk about the reactivity, tertiary alcohol is easier to dehydrate than compared to secondary alcohol, than compared to primary alcohol. So let's just take example of primary alcohol first. Primary alcohol requires 75% concentrated H2SO4 with 140 to 170 centigrade. Secondary alcohol requires 60% H2SO4 with 100 centigrade. Tertiary alcohol requires 20% concentrated H2SO4 at 85 centigrade. Alright. After that, we have dehalogenation. Dehalogenation requires, for dehalogenation, we basically use zinc with an anhydrous solvent like methyl hydroxide or acetic acid to produce alkene. All right. Another important point is Cobb's electrolytic method. So with Cobb's electrolytic method, we can also produce the alkenes. So essentially, we use a sodium or potassium salt of dicarboxylic acid. Succinic acid is the one which is mostly used, and that succinic acid again at the anode it will produce alkene. That would be symmetrical, and at cathode it will produce hydroxides. All right, and now let's just move on to the partial hydrogenation of alkyne, such that if we just partially hydrogize alkyne, we can get two types of alkene. On the basis of the catalyst we use, which is the cis alkene and trans alkene. So we can either get a cis alkene, we can or we can get a trans alkene depending on what type of catalyst we use. So uh, we if you're just going to use this, for example, if you're going to use palladium over barium sulfate, then at that point we are going to get a cis alkene. Then at that point we are going to get a cis alkene, and that can be poisoned by uh, quinoline, which is Lindlar's reagent, Lindlar's catalyst. And second is whenever we are going to take sodium in liquid ammonia at minus 33 centigrade, we'll basically get at minus 33 centigrade, we'll basically get a transalkene. Now, a transalkene is more stable than cisalkene because the similar groups are apart from each other. Alright, so now let's just move on to some of oops, some of the chemical reactions of alkenes. So let's just move on to some chemical reactions. First chemical reaction we are going to study is hydrogenation. Hydrogenation is something we have already studied. It's the same as the hydrogenation which was used to form alkane. Again, alkane would be produced, but in that case we are going to use a catalyst known as Raney nickel. Why do we use Raney nickel even though we can use platinum or palladium? Because Raney nickel is less expensive. Palladium and platinum are metals, and these are essentially noble metals due to which they are pretty expensive. So we rather use Raney nickel. It is obtained simply. We take nickel aluminum and um, soak it in a caustic soda solution, due to which we get the Raney nickel, and that Raney nickel is then used for hydrogenation as done previously. Hydrohalogeniation, it's pretty simple. We take hydrogen halide and then we add an alkene, um, due to which it forms alkyl halide. And then we have some important characteristics regarding uh, the reaction mechanism. Reaction mechanism. The for hydrohalogenation, whenever we are going to have, let's say this is an alkene, let's say this is an alkene. If it if we want to perform hydrohalogenation in it, then we need to consider the reaction in two steps, which is such that step number one, what actually happens is, in step number one, the hydrogen chloride comes. It can be any hydrogen halide, it can be hydrogen bromide, hydrogen chloride, but I'm taking the example of hydrogen chloride. Let's say it's a hydrogen chloride comes, and that's having a positive charge, right? It's having a positive charge, and over here there is a pi bond. So pi bond is having pi electrons, which means it's negative. So this hydrogen, this hydrogen, this hydrogen would be attracted towards the pi bond. It would be attracted towards the pi bond, due to which it will form a bond over here, due to which it will basically, what it will actually do is it will break the pi bond. It will break the pi bond. Oops. What it will essentially do is it will break this pi bond and come and attach over here. So what it will actually do is it will form this thing. It will form this thing, which is known as, and there would be basically what actually happens is there were two electrons right over here. It broke the pi bond, and it took basically both of the electrons were taken by it. So due to this, both of the electrons were taken by the hydrogen. Due to this, these electrons being taken by hydrogen, the chlorine, sorry, not chlorine, but the carbon over here will get a positive charge. And this entire carbon compound, which is having a positive charge, is known as a carbocation. Carbocation. And in the first step, what essentially happens is there's a formation of a carbocation. And in the second step, what happens is that in the second step, that carbocation combines with the negative charged chloride. Carbocation combines with chloride ion, negatively charged chloride ion, or we can also say that it will combine with a nucleophile, because it's a nucleophile, right? It's a nucleophile that we generated from hydrogen halide. So when carbocation combines with a nucleophile, then this will essentially produce the alkyl halide. So these are the two steps. Number one is formation of carbocation, and number two is joining of the carbocation with nucleophile. Now there's another method which there's a rule basically. Um, the addition of addition of the addition of hydrogen halide which we did over here was essentially in a symmetrical alkane, right? This was a symmetrical alkane. This is a symmetrical alkane, right? Over here, it's a symmetrical alkane. It's ethane, right? But if we want to do the same reaction on an unsymmetrical alkane, we obey a rule which is known as Markovnikov's rule. What Markovnikov's rule says is that whenever there is an whenever there is an addition of whenever there is the addition of an unsymmetrical alkene, you will always add the nucleophile on the carbon atom which is having the least number of hydrogens. The nucleophile will always be added to the carbon atom having least number of hydrogen. So for example, if you just look here, we'll find that for example, this is hydrogen bromide reacting with an unsymmetrical alkane. Then at that point, um, we might think that the nucleophile bromide would be added on the first carbon, but it would not be added on the first carbon. It would be rather added on the second carbon. Reason behind it is that second carbon is having least number of hydrogen atoms as compared to first carbon. First carbon is already having 3 number of hydrogen atoms, due to which we cannot add it on the first carbon. We'd rather add it on the second carbon because of less number of hydrogen atoms. So this is the essential concept. Now let's just move on to uh, the process of halogenation. Halogenation is again pretty simple. What we actually do is we add a halogen molecule to alkene in the presence of an inert solvent, carbon tetrachloride, because the reaction is pretty violent and we need to make it pretty inert so that an explosion might not happen. This actually results in the production of a vicinal dihalide, which is uh, having two halogen atom near a site. And there's another compound which is known as geminal dihalide. When two halogen atoms are attached to the same carbon, then it is known as the geminal dihalide. Anyways, let's just move on to this point that there are two steps to do this reaction as well. In the first step, what actually happens is that a halogen molecule comes. This is a halogen molecule which comes. Now we know that halogen molecules are non-polar. They are non-polar, right? They are non-polar. So what actually will happen is when halogen atom will come over here, this halogen atom comes over here, right? This halogen atom comes here. It will come here, right? It will come here. It will come here, over here. Halogen atom comes here. So when the halogen atom comes here, it is having a pi bond. It will come near to the pi bond, right? So that pi bond is negatively charged, and that the chlorine atom is also negatively charged. What actually will happen is the electrons of pi bond, the pi electrons will start to repel the electrons which are present in the chlorine atom, due to which these electrons being repelled by the pi electrons will tend to saturate the electron cloud towards the other chlorine atom, due to which the side which is approaching would be becoming positive, and the side which would be away from the pi bond would become negative. And due to this process is known as um, this process is known as uh, induced dipole production, similar to that, induced dipole. And basically what actually happened was chlorine was a neutral molecule. We just made it dipole with the help of induction, with the help of charge which was in the pi bond. Now what actually happens is this chloride molecule now combines with this ethane molecule. Again the same part happens. There is a formation, instead of the formation of a carbocation, there would be formation of a bromonium ion, sorry, the chloronium ion. So I take hydrogen here, hydrogen here, hydrogen here, hydrogen here. This is a bond, and there will be a formation of a chlor chlorine atom will come here, and that will basically form a cyclic ring which is known as a cyclochloronium ion. That cyclochloronium ion will have a positive charge. When it will combine with the nucleophile, which is the negative chloride atom, it will then produce in the second step. Then in the second step, what actually happens is the cyclochloronium ion combines with the nucleophile to produce the vicinal dihalide. So this is how the entire reaction happens. Again, Markovnikov's rule applies to here as well. So essentially we can do it then as well. And then we have hydration reaction. Hydration is a process where we basically, let's say if we take sulfuric acid, we take cold concentrated sulfuric acid, and then we put it in alkene. We take cold concentrated sulfuric acid and put it on alkene. We will get ethyl hydrogen sulfate as a result. When you're going to boil ethyl hydrogen sulfate at 100 centigrade, of course, then we are going to get the alcohols. This is the entire reaction. After that, we have hydration. This actually happens. This is a process in which the solvent also reacts, such that we take halogen molecules. We dissolve halogen molecules in water, due to which they form hydrohalides, due to which they produce hydrohalic acids and hypohalous acids. Hypohalous acids. Hydrohalous acid, sorry, hydrohalide acid and hypohalous acid. Now, what actually happens is the hypohalous acid over here reacts with alkene in order to produce a halohydrin. Halohydrin is having a halogen group and hydroxyl group. So this is about it. Now there's an important concept to understand. The reactivity is from fluorine, chlorine, bromine to iodine. But we do not use fluorine and we do not use bromine. We do not use fluorine because it's reactive, because it's too reactive. Because we don't use iodine because it's too unreactive. These are the ideal things which we use for the reaction. Alright, let's just now move on to alkynes. All right. Alkynes are hydrocarbons. Alkynes are hydrocarbons which have a triple bond. They have a triple bond. Now, if you just look into their structure, first its formula is CnH2n minus 2, and when it comes to the um, when it comes to some important characteristics of alkynes is alkynes are also known as acidic hydrocarbon, also known as acidic hydrocarbon. We're going to understand why some alkynes are also known as acidic hydrocarbons. Oops, what's happening? Why these are known as acidic hydrocarbons? So, if you just look into its structure, it's having an sp hybridized orbital, such that it takes its one s orbital, one p orbital, both of these combined together to produce the sp hybridized orbital. Sp hybridized orbital. Now, an important thing to consider over here is that if this is, let's say, a carbon, these are two carbons, right? I draw two sp hybridized orbitals. Two sp hybridized orbitals. One sp hybridized orbital is here. This is an sp hybridized orbital of this carbon. This is an sp hybridized orbital of this carbon. And I draw another sp hybridized orbital here. This sp hybridized orbital. This is right. This is the s orbital of the hydrogen. Hydrogen over here. Hydrogen over here. Right. This is s. This is s. This is sp. This is sp. And two of the layers now. Two of the orbitals are sp hybridized orbital for each carbon atom. One of the sp hybridized orbital form the bond with other sp hybridized orbital of the carbon, forming sp hybridized orbital, and second is sp s hybridized orbital. Now if we just take the strength of all of these, we just compare the strength sp hybridized orbital and sp s hybridized orbital. Which one is stronger? The stronger one is sps. Sps is greater than sp. This is an important thing to consider. Alright, so uh, now we are having two of the p orbitals which are unhybridized. Unhybridized p orbitals. Unhybridized p orbitals. Unhybridized p orbitals. Let me draw another p orbital. So these p orbitals form the pi bonds. They form the pi bond. So essentially there are two pi bonds in an alkyne, and there are 1, 2, 3 sigma bonds. 2 pi bonds and 3 sigma bonds of an ethyne molecule. Its lowest member is ethyne, also known as acetylic. Acha. Alright. And there's another important thing about this entire structure. There is another important thing about this entire structure. Let me just circle it. All right. So um, this is the entire structure. Each carbon atom is having has a capability to form two sigma bonds and two pi bonds. Each carbon can make two sigma and two pi bonds. Alright. So now let's just move on to the general properties. General properties here start from C2 to C4 as gases. All of them are colorless, odorless, except acetylene. They have a garlic-like odor. Acetylene has a garlic-like odor. C5 to C12 liquids, and C13 onwards they are solids. Now there's an important thing to consider, which is that the stability increases with the number of triple bonds. As the number of triple bond increases, the stability also increases. And now let's just look into another important aspect, which is the acidity of alkyne. Basically, alkyne is having sp hybridized orbitals. Sp hybridized orbital, and an sp hybridized orbital has 50% s character and a 50% p character, which means the maximum amount of s character in a hybridized orbital is in a sp hybridized orbital. So because of more s character, it has more capability to attract the electron towards itself because it has more nuclear attraction, right? Due to because s orbital is nearer to the nucleus, due to which it has a greater nuclear attraction, due to which the sp hybridized orbital due to which this sp hybridized orbital at this point, for example, I mean, like, if we take, let's say, example of we take example of propine, right? We take example of propine, right? So in propine there's an sp-sp hybridized or bond, sp-sp bond between carbon and carbon, and there is an sp-s bond between carbon and hydrogen. Now sp hybridized orbital is nearer to the nucleus, has greater attraction, due to which it attracts the electron cloud more towards itself. It attracts the electron cloud more towards itself. Attracts the electron cloud more towards itself. More of the electron cloud is attracted to the carbon, due to which it makes carbon partially negative and makes the hydrogen, which is attached at the terminal, partially positive. Now because that hydrogen is partially positive, it makes alkyne acidic. That makes alkyne acidic, and that acidic alkyne can then react with various compounds. It can then react with, let's say, hydroxides to produce salts, and in that way they can produce a lot of different they can produce a lot of different things. So uh, if we just take acidity in account, acidity acidity of alkynes is only possible in unsymmetrical alkynes, which are unsymmetrical, or terminal alkynes, while the alkynes which are symmetrical are non-terminal and they are non-acidic. So this is an important aspect. Usually we call the case that one alkyne has acidic characteristics. One alkyne, which means that there's a triple bond at the first carbon, which means that there should be an acidic hydrogen here, right? So this is an important aspect. Now we are going to do few reactions as well for the acidic hydrogen over here. So here we are with some reactions. Whenever we are going to, let's say, have ethyne, let's say if I'm not ethyne essentially, but if I'm going to, let's say, take any unsymmetrical alkyne and then react it with sodium amide in liquid ammonia, it's going to produce an acetylite. Acetylite. What is acetylite? Acetyl, basically it is the two carbon alkyne, which means acetyl, and ide is used for negative charge. Ide is used for negative charge, right? So whenever an alkyne gains a negative, is having a negative charge on carbon, then it is known as an acetylite. So, I mean, like whenever there's an ethyne gaining a negative charge on carbon, then it is ethynite or acetylite. But if it is any other alkyne, then it's going to be called as alkynide. So in this case, let's say if we take an unsymmetrical hydrocarbon, we put sodium amide in liquid ammonia, and we actually get disodium acetylite salt. Likewise, if we take ammonical solution in which we put cuprous chloride, and then we actually get dicopper acetylite, and that is a salt actually. And then we take silver nitrate, and when we react it with acetylite, then it will produce disilver acetylite. These are the neutralization reactions that happen. Acetylite is basically a weak acid. It's a weak acid. So for the weak acid, we need a weak salts. We need weak bases as well. Silver nitrate, cuprous chloride are very weak bases, so we are going to react it with those only. Now these can also react back. They can also react with various acids. They can react with mineral acids like sulfuric acid, nitric acid in order to regenerate alkynes. This entire methodology can be used for purifying alkynes, for you know the acetylites can be used for purifying, for identifying, for separating, for preparation of alkynes. Alright, so now let's move on to the preparation. That how can we prepare this? For preparation of alkyne, the first method we use is dehydrohalogenation. Dehydrohalogenation involves the removal of uh, a hydrogen halide molecule. So it can be removed in the presence of alcohol. We take potassium hydroxide in an alcoholic solution, and then the we'll essentially get the alkyne. It will actually first produce an alkene with bromide, which is known as vinyl bromide, and a double bond with a halide, which is known as vinyl halide, and that will further react with alcohol to produce the ethyne. So it will actually happen in two steps. Second method is dehalogenation. Whenever we are going to perform dehalogenation of tetrahalides, then they will produce the alkynes. For that, we basically take zinc and then we perform dehalogenation of tetrahalides. And another method is Cope's electrolytic method. When we are going to take unsaturated salts of dicarboxylic acids, then we can actually produce alkynes. At anode we produce free radicals. At cathode we produce hydroxides, which is potassium hydroxide at cathode, and at anode it produces the alkyne. Example of unsaturated dicarboxylic acid involves malic acid, which is produced. Alright. Another industrial method which is very famously used is with the help of calcium carbide. Basically, we take quicklime and we heat it up in an electric furnace at 2000 centigrade with carbon black. So essentially that produces calcium carbide. That calcium carbide can then, it's basically a cyclic molecule. Calcium carbide then when it is dissolved in water, it produces ethine and calcium hydroxide. It is used for the industrial preparation of ethine. So that's again pretty important as well. Now let's just move on to some of the reactions which are pretty important. Number one is hydrogenation. Hydrogenation of ethine can happen again through the same catalyst, nickel, platinum, palladium, at the same temperature. But if it is in the case of ethine, then uh, it will take place in two steps. In the first step, it will form ethene, and in the second step, it will form ethane. So it happens in two steps, and uh, at first, the removal of hydro the at first the removal of the pi bond and formation addition of at first the reduction of the ethine is difficult. Reduction of ethine is more difficult than ethene. Why? Because ethine is more stable. Yes, this is an again important factor which I did not mention, that uh, over here when we are taking an alkyne is having three bonds, triple bonds, due to which its bond distance is lower. Its bond distance is very low. Because of low bond distance, the nucleus are close together. The nucleus are close. And due to this, nuclear attraction is high. Nuclear attraction is extremely high. And because of the high nuclear attraction, there is greater stability. Because of greater nuclear attraction, there is greater stability in the alkyne molecule. So because of this reason, even though it is having two pi bonds, it is not that reactive because it is having shorter bond distance. Alkyne, oops. If you just compare it with alkane and alkene, then we can say that alkene is the most reactive because it is a pi bond and it is not having a shorter bond distance as well, then alkyne, and then alkane. So this is the order of reactivity. You need to keep that in mind. Alright, let's just understand the reactions. After that, we've got, after hydrogenation, we have the halogenation. If we are, if you are going to take if you're going to add halogen in the ethane in the presence of an inert solvent, we are going to first produce the dichloroethane, and then we are going to produce the tetrachloroethane. Um, uh, a, di a dichloroethene and then a tetrachloroethane. So this again happens in two steps, the two-step procedure. And then we have hydrohalogenation. Hydrohalogenation, in which again, when we are going to add hydrogen bromide, it will first produce vinyl bromide, and when we are going to further react vinyl bromide, it will produce dibromoethane. After that, we have hydration. Hydration actually happens pretty differently. For hydration, what we actually do is we we take mercuric sulfate, HgSO4, and we take H2SO4 at 75 degrees centigrade. At that point, we basically at 75 degrees centigrade, we add water into the ethine, due to which it produces vinyl alcohol. This compound, vinyl alcohol. Now, if you just take the structure of vinyl alcohol, it is this structure. This is the structure of vinyl alcohol. An important point to be considered over here, this structure, whenever there is a double bond with an OH group, double bond with OH group, then this structure is known as an enol group. So if you just take enol group is a very unstable group. It's also present in DNA, and that causes a lot of mutations, which ultimately leads to a lot of genetic disorders. But anyways, that is very unstable group, and that stabilizes itself to form the carbonyl group, also known as the keto group. So if it is, let's say, vinyl alcohol, then it's going to be the let's say if it is you know vinyl alcohol, then it's going to form the acetaldehyde. But if, let's say, it's having a greater number of carbon atoms, then it's going to form the ketones. Lastly, we have the addition of nitrates. Not lastly, but these are the addition reactions. After that, we have oxidation reactions as well. We basically, whenever we are going to add ammonia with aluminum oxide at 300 centigrade, we basically will get acetonitrile or cyanide. Or when we add hydrogen cyanide into ethane, we'll basically get with the catalyst copper chloride, ammonium chloride, we will get acrylonitrile. And then we have some oxidation reactions with alkyne. These are again pretty simple. The first oxidation reaction is with potassium permanganate oxide. For example, if we just take potassium permanganate oxide. Alright, so after doing the reaction oxidation reaction of alkyne we'll move back to alkenes. So when we add potassium permanganate oxide and alkyne, that gives us glyoxal. And that glyoxal is unstable, which further undergoes oxidation in the presence of potassium permanganate oxide to produce oxalic acid. So this is how oxidation happens. Second is combustion. Combustion again produces, whenever we are going to combust acetylene, it will produce a flame of oxyacetylene, which is used for welding purpose and for cutting of metals. Oxyacetylene flame used for cutting of metals or welding. After that, we have the formation of we have the polymerization reactions. Number one polymerization reaction is the formation of synthetic rubber. How does this form? Whenever we are going to polymerize ethyne in the presence of cuprous chloride and ammonium chloride, we are going to produce vinyl acetylene. Vinyl acetylene further polymerizes to form divinyl acetylene, which further polymerizes with the presence of HCl. When we are going to put divinyl acetylene, we first use vinyl acetylene under cuprous chloride and ammonium chloride, which produce divinyl acetylene, and the divinyl acetylene in the presence of HCl will produce chloroprene. Uh, Also, that chloroprene further polymerizes to form neoprene, which is a synthetic rubber. Alright, this is an important thing. And second is benzene formation. Now, when we are going to pass ethyne through a copper tube at 300 centigrade, it will produce benzene ring. These are certain reactions of alkynes. Now, let's just move back onto the let's just move back onto some oxidation reactions of alkene. These are the oxidation reactions of alkene. Now, whenever we are going to, let's say, if we're going to have ethene with oxygen, when we are going to take ethene and we are going to oxidize it through peroxy acid. Peroxy acid involves example of peroxyacetic acid, peroxybenzoic acid, peroxy uh, acetic acid or peroxybenzoic acid. Those acids which are having the peroxy group. Peroxy group, basically it is simply it's simply an oxygen atom in which the valency of oxygen atom is -1. So this is a peroxy group, and that peroxy group is very unstable. Whenever we are going to, let's say, take a peroxy group, I'm just taking it as oxygen over here, and then we burn it at 300 centigrade in the presence of silver oxide catalyst. We will get ethylene epoxide or ethylene oxide. This is known as ethylene oxide or ethylene epoxide. This is a three-membraned cyclic ring, as ethylene oxide or ethylene epoxide. So this is an important reaction. And then we have hydroxylation. There are two basically tests which are used for detection of unsaturation. Number one is halogenation, because in halogenation the brown color of bromine is you know converted into colorless when there is formation of alkyl halide, while in hydroxylation the purple color of potassium permanganate oxide is converted into colorless due to presence of ethylene glycol. Let's see the reaction actually. We basically take potassium permanganate oxide, that is a cold dilute around 1% concentrated potassium permanganate oxide, also known as Bayer's reagent. Bayer's reagent. That Bayer's reagent is used to oxidize ethene, due to which it forms ethylene glycol. Now, when the reaction completes, the purple color of potassium permanganate oxide disappears. It becomes colorless due to the presence of ethylene glycol, due to which this indicates that there is an unsaturation. After that, let's just move on to another one, which is combustion. Combustion is pretty simple. When you are going to burn ethene in the presence of oxygen, it will produce carbon dioxide and water, when it will release heat of combustion. And then we have ozonolysis. Whenever we are going to react ozone, which is an unstable allotrope of oxygen, with ethene, it will first produce a molozonide, and then that molozonide will rearrange to form ozonide. That ozonide, in the presence of zinc and water, will produce formaldehyde. In case of ethene, it will produce formaldehyde, and in case of hydrocarbons, in case of a high number of hydrocarbons, it will produce ketones. Now, the byproduct is hydrogen peroxide, which reacts with zinc in order to produce zinc oxide plus water. Now, there's another compound which is a reaction which is known as polymerization reaction. For polymerization reaction, we use 400 degrees centigrade, high temperature, high pressure, 100 atm pressure, to polymerize it into polyethylene. So these are all of the reactions. Now let us discuss few important commercial uses of some compounds, some pure hydrocarbons. Number one is methane. Methane is used for the production of chloroform, uh, for the production of chloroform, tetrachloromethane for the production of uh, you know for the production of alkyl halides, and methane is also used for as a burning gas, and it is also used um, as fuel. On the other hand side, if we just take ethene is basically, there's a lot of uses. Number one, ethene is a ethene is used as an anesthesia. It is used for ripening of fruits, and it can also be used for production of plastics. Polyethylene can be used commercially, and in the World War I there was a compound of ethene known as mustard gas, which was used to harm the soldiers. Basically, that was mustard gas. That was not actually a gas. It was a high boiling liquid, whose droplets were thrown onto the enemies, and that was a powerful vesicant which causes blisters. This is the entire structure of mustard gas. When we react sulfurous chloride with ethene, it will produce dichloroethyl sulfide or mustard gas. Sulfurous chloride with ethene produce dichloroethyl sulfide. Dichloroethyl sulfide, which is mustard gas. So this is an important thing. And acetylene. Acetylene basically, the oxyacetylene flame is used for welding, alongside which acetylene is used for PVC making, plastics making, for the production of synthetic rubber, neoprene, and acetylene is also used for making a lot of compounds like alcohols, acids, aldehydes can be produced with the help of acetylene. So this is all about today's video. I hope you enjoyed it. I hope you learned something really cool, and hopefully in the next video we are going to understand benzene. So if you have any questions, if you have any comments or any feedback to give, please feel free to share in the comment box. Thank you.